England, 1666. The plague has killed roughly 100,000 people in London alone over the past year. Cambridge University is closed. The roads between cities are dangerous and largely empty. In a farmhouse in Lincolnshire, a young man who should by now have a career mapped out and a place waiting for him in the academic world sits instead in near total isolation, writing in a notebook that he keeps in a locked box. In 18 months, he will have worked out the mathematics of how objects in motion behave, the nature of light and color, and the first version of the theory of universal gravitation. He is 23 years old. He tells almost nobody. It will be 20 years before the world finds out what happened in that farmhouse. He is born on the 4th of January, 1643, in a stone farmhouse in Woolsthorpe, Lincolnshire, 3 months after his father died. The father, also named Isaac Newton, was a farmer who could not sign his own name. He never meets him. His mother, Hannah Isco, remarries when Isaac is 3 years old, moves into her new husband's house in a nearby village, and leaves the boy with his grandmother. He is not taken along. He has not seen his mother for roughly 8 years. This is the fact that Newton's biographers return to most often because Newton himself returns to it. In a list of sins he writes as a young man, somewhere between a private confession and an accounting of his own character, he includes threatening to burn his mother and stepfather in their house. He is probably 11 or 12 when he writes this. The stepfather is dead by then. The anger is not. He is a solitary child, not particularly strong, not popular with other boys, given to building things with his hands and thinking about things in his head. He builds model windmills and water wheels. He makes sundials. He keeps notebooks of observations about the world that his grandmother does not know what to make of, and his school teachers find either impressive or strange depending on the day. His mother returns after her second husband dies and brings him home to Woolsthorpe. She wants him to manage the farm. He is a poor farmer. He forgets to check on the animals because he has been sitting under a tree reading. The sheep get into the neighbor's garden twice in a single week. His uncle, who has a degree from Cambridge, notices something in the boy and argues that sending him to university would be less wasteful than keeping him on a farm. His mother agrees, eventually. In 1661, Isaac Newton arrived at Trinity College, Cambridge, as a Subsar, meaning he earned his keep by waiting on wealthier students. He is 18 years old and largely unknown to anyone there. That does not last long. Cambridge in 1661 is teaching Aristotle. Newton reads Descartes instead, then Galileo, then Kepler, working through the modern natural philosophers on his own time while attending the official curriculum with enough effort to pass and no more. By his third year, he has gone considerably further than his tutors. He keeps this largely to himself. The plague years of 1665 and 1666 sent him home to Woolsthorpe, and what happened there has already been described in the notebook he keeps locked away. When he returns to Cambridge in 1667, he is elected a Fellow of Trinity, and in 1669 he is appointed Lucasian Professor of Mathematics, a chair so prestigious that its previous holder steps down specifically to make room for him. Newton is 26. His first lectures are on optics. He has been working on light since the prism experiments at Woolsthorpe, and what he has concluded contradicts everything currently accepted on the subject. In 1672, he presented his theory to the Royal Society of London, his first public scientific communication, and the reception was not what he expected. Robert Hooke, the Society's chief experimenter, a brilliant and combative man who has built his reputation partly on his own optical work, reads Newton's paper and sends back a detailed critique, dismissing its central conclusions. Hooke is not entirely wrong in his objections, but his tone is that of a senior man correcting a junior one, and Newton receives it that way. The response Newton sends back is cold, precise, and devastating. He dismantles Hooke's objections one by one with a methodical thoroughness that makes clear he has anticipated most of them and finds them inadequate. Hooke does not back down. Newton, furious, withdraws from public scientific communication almost entirely, telling a colleague that dealing with the criticism of men who have not understood him is not worth the trouble of publication. He publishes almost nothing for the next decade. The feud with Hooke will last until Hooke dies. In 1684, the astronomer Edmund Halley traveled to Cambridge with a question that had been circulating among the Fellows of the Royal Society for months without a satisfactory answer. If the force holding the planets in their orbits weakens with the square of the distance from the sun, what shape would those orbits be? Newton tells him the answer immediately: an ellipse. Halley asks how he knows. Newton says he has calculated it. Halley asks to see the calculation. Newton cannot find it in his papers, but tells Halley he will redo it and send it. He sends it. Halley reads it and understands, with a clarity that leaves him shaken, that the man sitting in that Cambridge study has solved a problem that the best mathematical minds in Europe have been working on for years, and has done it so thoroughly that what he has sent is not a solution, but the outline of something much larger. He travels back to Cambridge and asks Newton what else he has. What Newton has is the Principia Mathematica, though it does not have that name yet, and does not fully exist yet in any form that another person could read. Over the next 18 months, Newton writes it. This is not a straightforward process. He works at his desk for days at a time, sometimes forgetting to eat, sometimes leaving food on his plate untouched because he has gone back to his study before finishing it. His assistant, Humphrey Newton, no relation, later recalls that he rarely saw him laugh, that he seemed to sleep very little, and that during the writing of the Principia he appeared to be somewhere else entirely, even when he was physically present. The book is published in 1687, with Halley paying the printing costs because the Royal Society had spent its budget on a history of fish. It sets out, in rigorous mathematical language, a complete account of how objects move and how they attract each other across space. It explains the tides, the orbits of the planets, the path of comets, and the behavior of objects in motion on Earth within a single unified framework. Nothing like it has been written before. The Principia changes Newton's life in ways he does not entirely welcome. He is famous now in the specific way that a man becomes famous when other men of comparable intelligence read his work and cannot find fault with it. Letters arrive from across Europe. His name circulates in the scientific academies of Paris, Berlin, and Amsterdam. He was elected to Parliament as a representative of Cambridge University in 1689, sat for a year, contributed almost nothing to the proceedings, and returned to Cambridge without apparent regret. What does not arrive with the fame is peace. Gottfried Wilhelm Leibniz, a German mathematician and philosopher of considerable ability, has been developing his own version of calculus independently since the 1670s. Newton has been working on what he calls his method of fluxion since the plague years, but has published none of it. Both men have arrived at essentially the same mathematical tool by different routes, using different notation, and neither is willing to accept that the other might have done so independently. The dispute begins quietly in the late 1680s with a series of letters and published remarks that are technically civil and practically hostile. Each side accuses the other of having seen private correspondence or unpublished manuscripts and built on them without acknowledgment. The accusations are never fully proven in either direction. What is certain is that the disagreement, once started, does not stay quiet for long. Newton files it away. He is patient in the way that people are patient when they have not yet decided to be otherwise. The reckoning with Leibniz will come, but not yet. What comes first is a collapse. In the autumn of 1693, Newton wrote 2 letters that alarmed everyone who received them. The first goes to the philosopher John Locke. In it, Newton accuses Locke of having tried to embroil him with women, and of being a hobbist, meaning someone who does not genuinely believe in God. Neither accusation has any apparent basis. The second letter goes to Samuel Pepys, the diarist and naval administrator, and tells him that Newton is in a condition of extreme disturbance, that he has not slept more than 5 hours a night for several weeks, and that he no longer feels fit for human company. Both men write back with concern. Newton responds to each of them with an apology, saying he cannot account for what he wrote and that he believes he was not himself. What caused the breakdown is not known with certainty. The most widely accepted explanation, supported by analysis of hair samples conducted centuries later, is mercury poisoning, the result of years of chemical experiments in which Newton regularly heated mercury compounds in enclosed spaces and sometimes tasted his experimental materials. He was also, by 1693, under sustained pressure from several directions at once. The Leibniz dispute was sharpening. His attempt to secure a government position had come to nothing after years of effort, and a close friendship with a younger Swiss mathematician named Nicolas Fatio de Duillier had recently ended for reasons Newton never explained. He withdrew almost completely for 2 years. He does not publish. He does not lecture. He corresponds minimally and with evident effort. The man who wrote the Principia in 18 months of ferocious concentration sits largely still, and the scientific work, which has defined every waking hour for 30 years, stops. When he comes back, he is not quite the same person. He is harder, more suspicious, and considerably more interested in destroying Leibniz than he was before. In 1696, Newton leaves Cambridge for London and takes up the position of Warden of the Royal Mint, a job that most people who know him assume is a comfortable sinecure, the kind of undemanding official role that distinguished men are given as a reward for distinguished careers. Newton treats it as a military campaign. England's currency is in serious trouble. Decades of coin clipping, the practice of shaving small amounts of silver from the edges of coins and passing them on at face value, have degraded the money supply to the point where the economy is straining under the weight of currency nobody trusts. The solution is a complete recoinage, melting down the existing coins and minting new ones with milled edges that make clipping visible. Newton throws himself into the logistics with the same focused intensity he brought to the Principia, overseeing the output of the mint's furnaces, reorganizing its workflows, and driving production to levels it has never reached before. He also hunts counterfeiters. This part of the job is not in the formal description, but Newton pursues it with a personal investment that goes beyond professional duty. He disguises himself and visits the taverns and prisons of London where counterfeiters operate, gathering evidence himself. He studies handwriting, tracks informants, and builds prosecutorial cases with the same methodical precision he applies to mathematics. He sends at least 28 men to the gallows. The most significant of them is William Challoner, a skilled counterfeiter who makes the mistake of publicly accusing Newton of incompetence and attempting to have him removed from his position. Newton spends 2 years building the case against him, working around every legal obstacle Challoner places in his path, and watches him hang in 1699. Meanwhile, the war with Leibniz has moved from letters to institutions. Newton becomes president of the Royal Society in 1703, the year Robert Hooke dies. The timing is not lost on anyone who knows the history between them. One of Newton's first acts as president is to publish his Optics, the work on light and color he has been sitting on for 30 years, partly because Hooke was alive and would have responded to it, and Newton did not want the argument. He also commissions an official investigation into the calculus priority dispute with Leibniz. The investigation is conducted by a committee of the Royal Society. Newton writes most of the report himself, without disclosing this to anyone. The report finds entirely in Newton's favor. Leibniz appeals to the Royal Society for a fair hearing. Newton, as president, controls the process. Leibniz died in 1716, still fighting the case, attended at the end by his secretary and no one else. Newton reportedly receives the news with satisfaction. He was knighted in 1705 and spent his final years in London presiding over the Royal Society with an authority that discouraged disagreement and revising his major works for new editions with close attention to priority claims and personal slights he had been carrying for decades. He removes acknowledgments of other men's contributions in places. He adjusts dates. He's not a gracious victor. His health declined slowly through the 1720s. He stops attending Royal Society meetings in 1725. He refuses surgery for a bladder stone on the grounds that the procedure itself might kill him, which at the time is a reasonable calculation. He stops sleeping through the night. He stops eating much. He died on the 20th of March, 1727, in his sleep, at the age of 84. He never marries. He leaves no children. He is buried in Westminster Abbey, the first scientist to receive that honor, and Alexander Pope writes an epitaph that circulates across Europe within weeks. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light.